Good morning and welcome back to the live stream of the lecture Advanced Image Synthesis. And today we'll have our first new topic when we compare this to the computer graphics lecture from last semester. And today's topic will be reflections. So, what is reflections? Why do I talk about reflections? Well, reflection is part of this concept of inter-object realism. When you look at the way that the rasterization pipeline works, I mentioned the last time already a key concept, and that is the key concept that makes rasterization so well suited for hardware and well suited for parallelization is the idea that everything is independent from each other. So we treat every vertex separately. We then combine a bunch of vertices into primitives such as triangles, rasterize each triangle separately, then use those triangles in the rasterization process to generate fragments, then process each fragment separately, and finally write them into the frame buffer. When we write them into the frame buffer, we again just consider each fragment on its own and just compare this fragment to the pixel value in the frame buffer. So the basic idea is never consider any sort of interplay, or as few as possible, as to create literally thousands or tens of thousands of processors, put them on a silicon chip of today's graphics cards, and then run this at very high bandwidth. Okay, so that's the basic idea. This is why rasterization is so fast, in particular compared to other approaches. Other rendering approaches such as ray tracing, which can also be parallelized nicely, but does require a lot of information. Sometimes requires a crosstalk between different parts of the scene. So that has the huge advantage of speed due to parallelization, but has the huge disadvantage that there's a lot of inter-object effects that we cannot easily handle, such as shadows or reflections. Right? Both the shadow as well as the reflection. Oh, what's going on here? Okay, both shadows as well as reflections require, well, more than one thing. Right? The shadow requires a shadow caster as well as a shadow receiver. Okay, so two things. And when I say things, that might actually be a pretty big part of the scene, right? So there might be a whole, say, city. Just give me a second. I got something in mind. Go on, get out. City dust. Okay, I guess I got it fixed. Okay, let's say you have a city, right? Then your shadow caster might be, well, the entire city, even if it's just for a small patch in the scene. Okay, so potentially you need to assume that the entire scene has an effect. And with the reflection or refraction, it's the same, right? If I look at, for instance, the ring here, for any point, any pixel, any fragment of the ring, there's a chance that anything else gets reflected at that point. So I need to consider at least potentially the entire scene. And that, well, requires communication. So how can we fix that? Well, one approach is we say, well, it's not possible. We need to use a different rendering approach here. So for instance, ray tracing or something else. And that is what graphics vendors are trying to sell you these days, that there's only one way. You got to buy a new expensive graphic card to be able to get these effects. But, well, that is not entirely true. So let's look at what we can do without using a different rendering approach. Per se, there's nothing wrong with using a ray tracer or a ray caster or anything else, a path tracer or a radiosity renderer. Those are all systems that have their advantages and disadvantages. However, staying as long as possible within one rendering system has the huge advantage that you can reuse the same data structures because you're just using one concept, and that if this concept is specifically tailored for a certain architecture, say a certain piece of hardware, then you can stay on that hardware for a while longer. So that generally makes things more efficient. Okay, let's see what we can do without using a different rendering approach. And what I want to do here today is to look at a few specific types of reflection, so to say. And the first one is reflection at planar surfaces. Okay, so here we've got a few examples. We've got, well, planar mirrors or just objects that happen to be planar and reflect the scene to some degree. Here you can also see a sphere reflecting the environment. More on that in the second act. So first, let's look at the planes. Let's look at planar reflections. And the idea to handle this is based on this idea that, well, we don't necessarily, if we have a planar reflection, we don't even need to consider the mirror as part of the scene. We can simply just pretend that there's a mirror world. Okay, so we have on the left side here, we have the actual scene, right? It's made up of a bunch of spheres or circles in 2D. And on the right side, where the mirror is in the center, I say, okay, well, what if we just copy the scene? We literally mirror the scene around the center, and we'll just pretend, well, there's another scene that just happens to be exactly the same, except for the fact that it's mirrored. Okay? Notice that a mirror, even when it's planar, is generally not an infinite plane, right? So I actually depict this here. So when this is my viewing position and this is the mirror, then there might be parts of that plane that are not a mirror. So for instance, that are a wall or that are simply empty. Okay, so some of the pixels that I see do not see the reflected scene, okay, because they get blocked or they simply don't hit the mirror. Okay, so we need to take that into account later. But if we ignore that fact for a second, that a mirror is generally not an infinite plane but a finite plane, in that case, we can say, well, what if we simply copy the scene to the other side, mirroring it, and we're good to go. No mirror harm, still we get the same result. Okay, well, let's see if we can do that with our rendering pipeline, with our rasterization pipeline easily. So let's consider the following situation. Remember, we're only processing vertices. So when we're dealing with triangles, it's just a set of vertices. When we're dealing with quadrilaterals, it's just a set of vertices. And I could continue this forever. So the only thing we care about, at least in our rasterization pipeline that I described here, are vertices that finally make up the geometry. Okay, so, and since we consider them vertex by vertex, let's just do that. Let's just consider a single point, a single vertex that I call Q here. So we've got that point here, and we just want to know, well, where would that point end up if I want to mirror it at this plane here, at this blue plane. Okay, and well, this is the point, and this is the mirror point that I'm looking for. How do I figure out that its position? Okay, let's look at a few quantities. We need to know where the mirror is located, and we need to know its orientation. Otherwise, we can't do the whole process, right? So we need to know that part of our scene setup. And I just want to specify the mirror here as a point P. So I just need to know any point. It doesn't really matter which one. So I just want to know some point on the plane, and any will do. And that will give me its location. And then for the orientation, I just want to know the normal. Okay, so two quantities that I have to that have to be known about the mirror. That's a point and the normal. If you specify the mirror differently, say you specify it as a quadrilateral, no problem. Well, there's two, for instance, you just pick two sides of the mirror in the quadrilateral, compute the cross product, that will give you the normal. And then just pick any of the vertices of the quadrilateral as your point P. So it's fairly easy to turn any representation into this one here. Okay, well, let's assume we have this normal and this point P. What do we need to do? Well, let's make this a little bit smaller and then figure out the mathematical basics here, which aren't really a big deal. So the first thing I want to do is I want to compute the distance. How far is a point away from a plane? So this is a typical point-plane distance computation, which you should have done years ago or should have learned years ago at school. So what does it take? Well, you simply take the vector v, which is the connection of your arbitrary point to Q. I put this in the graphics, top left, right? So this is just a point. Since P is pretty much arbitrary, we don't really care about V itself, because it can also be pretty much arbitrary. But what we do care about is what happens if I project V onto N. So I take the perpendicular part of V, perpendicular to the plane. Okay, so that's the offset, right? The V, I can always decompose that into two components, one that is parallel to the normal and one that is parallel to the plane. Okay, and the two together make up V. How do I figure out the part that is parallel to the normal? Well, that is simply the dot product. Okay, so if I compute the dot product between this vector V and the normal N, I get the part, specifically the length. So that's a scalar, right? The dot product is always a scalar. That's the length along N. Or in other words, that's the distance of the point. Okay, the distance to the plane. And here I spell this out. So that is Q minus P, that's V dot N will give me the distance. Okay, next one is, what is QM then? Well, QM is simply starting at Q, taking twice that distance, okay, which is the distance from one side to the other, and the distance on the other side, and multiplying that with the negative normal. So we start at Q, we subtract the normal once, which means we're now on the surface, and then subtract it another time, so we're now on the other side of the mirror. Okay, so that's the computation we need to do to figure out QM. Now, we don't really want to execute this computation this way in the shader to compute every part. We could, but there's actually a more clever way. Okay, so first of all, let's take this computation that computes QM and just rewrite it a little bit. So all I basically do is I multiply it out. Okay, I'll multiply the outer brackets out by minus 2n. Okay, that's what I get out. And then I just, since it blows up a little bit in size, I want to simplify this a little bit and call P times NK. Okay, you'll see in a second why I do this. So now, let me get myself out of the way for a second. Now what I can do is I can simply rewrite the last of the equations at the top. I simply rewrite that as x, y, and z component. Okay, so it's literally the same equation 3 times, except that one works on x, one on y, and one on z. Okay, so why would I do that? I mean, if you compare the second equation on the top right with a 3 at the bottom, it doesn't really seem like that's a smart idea. Right? I turn a very short one into 3 longer ones. So why would I do that? Well, let's blow it up even a little further. And what I did here in comparison to the previous slide was I simply sorted the terms. So I sort all equations by the q's. So you see the first one, let's just focus on the first one. So we got QMX, that's QX times something, minus QY times something, minus QZ times something, plus something without the Q's. Okay, so, and the same I do for the QMY and QMZ version. So it's now sorted by the Q's. Okay, well, now what's the point of doing this? Well, if I sort it by the Q's, then I can simply rewrite this in matrix vector notation. I might actually fit here. Yeah. So I simply rewrite this in matrix vector notation because I know it's now sorted by the q's, well, and of course a constant part. So that the first part is multiplied by qx, second by qy, third by qz. And this allows me to write this as a matrix vector product. Now, again, you could say, boy, what's the point here, right? So this thing here, there's a typo in the third equation, is there? Really? Where? This is a joke? No, if there's one, I would actually fix it, but literally QY. So it says, let's say, where's the QX, QZ? Oh yeah, so that should be, yeah, you're right. Nice spot. So this should be a QY here. Yeah, correct. Looks like a typical copy and paste issue. Yeah, so that should be a QY. And here as well, obviously. This one's correct though. Okay, yeah, good thinking. Let me fix the slide. Not yet, but I'll fix them and put them back online. Okay, cool. So still, this one's now correct because it says QY here. what's the point of this thing here, right? So this is quite obviously a much more complicated representation than the initial one. There's yet another. And then QZNZ, and the end should be QZNZ. Okay, okay, yeah, there's also, geez, what happened to me when I print this? Yeah, so this one is, it should be a subscript, QZ, yeah. So I guess I was probably a little tired when I copied the last equation, yeah. So this should be K, not Q, K subscript Z. Yeah, there's no KZ in the whole equation anyhow, yeah. Okay, good. Continue. I'm actually using these slides for a couple of years now. No one ever noticed that, including me. Yeah. Maybe because the important one. No. Yeah. So if you find typos, please let me know. I'd like to eradicate them. I'm pretty sure that this is correct. So at least the issues that you spotted, I can see that they're okay here. So this thing is complicated, is long. So what's the point? Apparently, even for me, writing it down causes a lot of typos. So why would I go through all this trouble? Well, why would I go through all this trouble? Because now I managed to take a computation, an initial computation, which was the turn a vertex into a mirror vertex. And of course, that works for any vertex. So in other words, turn the scene into a mirrored scene. If I apply the computation to all of its vertices, I can then convert an entire scene. I used this like shifting back and forth trickery to turn this computation into a matrix vector multiplication. So why is that cool? Because we multiply the vertices with a matrix anyhow. Remember, there's this thing, model, view, and projection. Those are all matrices. And I multiply each and every vertex anyhow with parts of them, or the entire pipeline. Now, all I have to do to render the mirrored scene is I have to take that model view projection matrix and multiply it with this mirror matrix. Okay. What is the result? Well, it's just a 4x4 matrix, so it doesn't blow up or get more complicated or anything. It was a 4x4 matrix previously, model view projection. And now it's, well, model mirror view projection to be precise. If I do this, same work as before, like literally zero overhead. Okay, whereas the computation previously would have to be executed on top of what I do before. So this way I can do the entire rendering process without any overhead. Not the complete scene, that of course has some overhead because I need to render the normal scene and the mirrored scene. But the mirrored scene itself is as complex or as computationally intense as the scene itself. So you would expect a loss in performance of at most 50% or half. Okay, so it should drop to half the performance at most. Why at most? Well, we'll see in a second why it might actually be better. Okay, so let's look at the entire approach for a second. So first of all, we store the model view matrix. We compute the model view matrix. Then we multiply this with the reflection matrix. And then we render the scene. So that'll effectively render the mirrored scene. What we then usually do is we disable writing into the color components of the buffer, of the frame buffer, right? Remember, frame buffer is RGBA, which are these 4 color components, red, green, blue, alpha. It's a depth component and it has a stencil component. Okay, so what I now do is I want to disable any color writes. I render the mirror itself. What's the effect of that? Well, since I disabled color writes, it doesn't change anything about the picture itself. But the picture is more than just the colors, it's the depth as well. So when I render the mirror, this now writes its depth value into the buffer, effectively making sure that nothing behind the mirror from the original scene. I mean, of course, your room might continue after mirror, right? If I have a house and I have a mirror, there's usually something behind that, right? There's another room, potentially. And I want to avoid that this gets rendered. So I basically just write the depth footprint of the mirror into the buffer. Then I re-enable the color right and pop the model view matrix, effectively removing the mirror matrix component, and then I render the unreflected scene. Okay, so that makes sure that nothing of the reflected scene ends up being behind the mirror plane. So, and that gets it almost right. So that's almost correct. Why is it only almost correct? Well, there's this thing with this finite mirror argument from before. So here, when you look at these two scenes, so that's supposed to be a bunny on a plane in front of a mirror. Okay, so here's the right side is the actual scene, and the left hand side should be the mirrored scene. And everything you see rendered in blue here is inaccurate. Okay, so you see that these parts, when this is the mirror, I want to see the mirrored bunny here, but none of this should be visible. The same here, none of this should be visible, right? In particular, the mirror scene extends towards the real scene, and well, yeah, there's a couple of things that are incorrect. What I would like to see is something like this here, so everything else should be chopped off. Now, how can we make sure that only parts at a certain place on the frame buffer get rendered and everything else get discarded, regardless of what we render? Well, that is exactly what the stencil buffer is good for, right? Remember, the stencil buffer was a buffer that I can initialize in the frame buffer, and then I can then use to selectively discard fragments, just depending on their on-screen position, independent of what the fragment otherwise wants to do. Okay, so this is why this here is an ideal example for using the stencil buffer. So what I do is you first would initialize the stencil buffer so that only the mirror itself, not the mirror plane, but only the mirror itself changes its stencil value. Say I initialize everything to 0. Okay, let's just look at a little bit of OpenGL code here. So first of all, I clear everything and initialize everything to 0. Then what I can do is, for instance, I can draw the scene without mirrors. So I just draw my actual scene. The next thing I do is I disable color right again. Right? So that's basically color mask 000. So this is now disable color right in OpenGL lingo. And then I set the stencil operation. So that's what happens in the stencil test. I set it to a trivial test, which is always. So no stencil test is enabled itself. But I tell the system to replace any buffer that's in the stencil. Never mind the keeps here. So that's what happens if a test fails. Or so let's just focus on that replace here for a second. So we want to replace the stencil buffer by 1. So that's what the next parameter geostencil func says. Then I draw the mirror. So this effectively, since I say always, so there's no chance for the stencil test to fail, that effectively doesn't change anything about the color, but it changes the stencil value to 1 wherever the mirror was drawn. Okay, and everything else is still 0. Okay, so the next thing that we do is a little bit of tricking to make sure that we don't have any depth values at the mirror for a second. Okay, never mind this part for now. The next thing we do after that is our is the rendering of our mirrored scene. Okay, so we push the reflection matrix, draw the scene. So the first OpenGL call just basically undo what I did before. There's one other call here, okay, that I haven't mentioned so far, and this is this clip plane. So what does that do? Well, with the clip plane, you specify a plane that assures that on one side of the plane your scene gets rendered and everything on the other side gets clipped away, and everything that crosses from one side to the other will be chopped off. And that I also set to the mirror plane. That is to make sure nothing stands out of the mirror. Okay, even if it's in front of the mirror, it should never stand out. So this is why I set this clip plane. Then I draw the reflected scene, undo my matrix, my reflection matrix. So I now have the original matrix in there. I again disable color right and make sure that I have that my stencil buffer at the mirror is okay by just writing again now a 0 into the area where the mirror is. So what that assures that after I've rendered the scene and the reflected scene, again, the entire stencil buffer is 0. Why would I care? Well, because there might be multiple mirrors. So now I can repeat this process for the next mirror. Okay, so that means if I have 2 mirrors, for instance, I have to render quite a lot of geometry because I have to, for one mirror, I render the scene and the reflected scene. And for the second mirror, well, I have to again render the scene and the reflected scene and the scene and the reflected scene, right? Because the mirror might potentially see both sides. So you end up with a growing number of reflections, and that's exactly what you want. So if you have 2 opposing mirrors, that's what it's supposed to look. And this here on the top above me, that's what the scene will actually look like, right? So I end up copying the scene and its reflection back and forth. And that will actually create a bunch of overlaps. So I should you should not render redundant parts of the scene. But it's very well possible. And why? Why did I say at most it costs twice as much? Well, this here, of course, that's 1, 2, 3, 4, 5, 6, 7, 8, if I just counted them properly. The red one, by the way, that's the actual scene. Everything else are copies. So why did I say at most 8 times? Well, because not everything is visible. And and due to the fact that you might discard a ton of fragments if you don't see the reflected ones, this might actually speed things up considerably, depending on how much fragment work you do in your shader. Okay, so, but kind of the bird's eye view take-home message is, if you want to render a mirrored scene, you just copy the scene, and this copying basically means rendering the scene twice plus 1 matrix that you multiply to the original matrix, right? So 0 overhead, and you set a bunch of parameters, okay? So doing this, again, from a bird's eye perspective, apparently you need to fiddle around with the depth buffer, you need to fiddle around with the stencil buffer, and you need to set this clip length. But those are all things that you do once, and then, well, they sort of work. Okay, so that's one way to approach this. Has the nice drawback that it's very high quality. Since you render every part of the scene to the original frame buffer, you get the maximum resolution. If your frame buffer is super high resolution, you render an 8K image, you render all these things in 8K, so in very high quality. If you get close to the mirror, no problem, there's no aliasing, whatever, because you re-render the scene. So it's always at the optimum resolution. There's an alternative approach, which is pretty much worse in just about every regard that you can think of. Performance, quality, pretty much the 2 metrics that we care about. So what's the idea here for this alternative solution? That is, instead of mirroring the entire scene, we can also copy the camera to the other side of the mirror. So we can mirror ourselves and check, okay, how do we perceive the scene from the mirror? Then I take a photograph, kind of sitting inside the mirror, I take a photograph, and then I copy that photograph onto the surface of the mirror, okay? So you kind of take a picture of what the world looks like from the mirror's perspective, and then you simply hang that picture to the wall, so conceptually. Okay, so what does that take? Well, as I said, it does have a whole set of drawbacks. The first one is, when you take that picture, well, you need to store that picture. There are possibilities, and we'll talk about those in the exercises, to render into a texture. So you can basically, instead of rendering to the frame buffer, you can say, okay, well, this is a texture now, and I want the image to be rendered to that texture. Okay, so you can render to a texture which you can later use to apply it to a surface. So it's possible. However, when you do this process, you have to decide what resolution you want to use, right? That texture has to have a resolution that you need to decide on. So that's Act 1. It requires additional memory, which the previous solution doesn't. Second thing is that memory, you have to fix that somehow. So say, well, okay, I do a 2K by 2K texture here. Now, if you move close to the mirror and inspect it closely, like literally your camera moves very close to the mirror, then you only see a potentially tiny fraction, which means that there might be only very few of your texels visible, which creates, well, aliasing artifacts, right? You will see some sort of staircasing, or you will notice the resolution of the texture at one point or another. So It's also quality-wise worse. Okay, so it requires a ton of state changes. You need to set the texture, you need to disable the texture, all those cost time, so it's also slower. Okay, still, you can do it if you want, and here's the math to change the viewing direction and the camera's position. And if you look at those closely, they're pretty much the same computation as before, which is no surprise. We now just mirror another point. Now, why do I even mention that? If it's worse in quality, performance, and it also introduces more memory requirements. Because, and now comes the fun part, this is the thing that everyone uses. So if you use a game engine or anything, there's a super high probability that that's the approach that is taken, not the one that I mentioned previously. Now you might say, why? And again, the answer is fairly simple. It's easier to implement. Okay, it's way easier to implement. The reason being is that it requires you can better separate out different parts of the process. Here, I render the scene from the mirrored perspective, and I store this as a texture. And then I forget what I did, and I just render the normal scene, and I just apply this texture to a surface. So I can literally render the scene, then delete all states, clear everything, including the frame buffer, and then render the scene normal and use that texture. And that is a huge simplification if you want to write rendering code. If you can do one thing and then clear everything out and then do another thing, okay? Whereas the previous solution, even though it's much higher in performance, or it's higher in performance in particular, much higher in quality, it's more work because you got this interplay, right? You have to render kind of both parts. You have to make sure that the stencil buffer is properly initialized. And as your system grows and grows and grows, you will have more of those interplay things. And the complexity of the code, the complexity to debug it and to maintain it just grows exponentially because you have to check every combination. And it can be so hard that most people would actually say, okay, well, the quality sucks and the performance is bad, but at least I can maintain it. And there's a higher probability that it runs without bugs, which is kind of a funny argument if you think about it. It's something that you rarely encounter in computer science, that someone would say, well, okay, I take this route that is obviously inferior, but I can maintain it easier. And not everyone would say, well, learn how to program. Okay, but for computer graphics, the complexity is so high that we will actually see this notion pretty often in this lecture, that an inferior solution is preferred over a superior just for the sake of simplicity. Okay, and literally the simplicity of implementation, it's not a numerical problem or anything, right? The opposite is quite the case. It's numerically way more stable, right? But it's literally lack of programming skills, I would say. Okay, so now, all I talked about so far are planar reflections. So what about non-planar things? Spheres or, well, I don't know, whatever that object is. Crazy objects. Okay, anything that's not a plane or not close to a plane. Okay, now let's call this Act 2, and let's again focus on something that is almost spherical, okay, or sphere, or a point, okay? Something that is pretty spherical. Okay, so what can we do if we have a point? Let's just assume the sphere is also pretty tiny, and let's just say it's a point. It's a point that sits somewhere that reflects the environment. Okay, what you can see here, by the way, that's a rendered scene with a bunch of reflected spheres, and this is a photograph with two rendered objects in it. So the technique that I'll show you works for both artificial scenes, reflections of artificial scenes, as well as reflections of real world photographs. Okay, and we'll see what this mirror ball in the bottom left has to do with this. So we want to use our environment maps. So what is an environment map? Well, an environment map is a map about the environment. Great. So it's a representation about the environment around a specific point. Specific point is kind of the key word here. And that is what this sphere represents here. As a matter of fact, this sphere is also a photograph. So this is taking a mirrored sphere, just like, you know, from your Christmas tree setup. It's a mirrored sphere. It's generally the only difference from the Christmas ball is that it's usually coated in silver on the outside rather than the inside, so you don't get the properties of the glass. So this is just a metal sphere that's highly polished, and then you take a photograph of that metal sphere. Okay, so effectively, we just take a single picture, and what does this picture contain now? So if you crop away the part of the photograph around the sphere and just care about the reflection on the sphere, what we get is a representation of the environment, right? And that's why we call it environment map. What's kind of interesting about this is when you literally think about this for a moment, you're standing in a room, you put a metal sphere, like a Christmas tree ball, you put that in the center of the room, right in front of your eyes. And you look at that sphere, how much of the room do you see? Okay, how much of the room do you see on the sphere? Not around the sphere, just on the sphere. If you crop everything away, just look at the reflection on the sphere. How much of the room do you see? Okay, well, you're standing here, there's the sphere. How much do you get? Do I get like, I don't know, half of the room? I don't know, a quarter, everything, right? Any suggestions? How much of the room do I see reflected in the sphere? So I can give you the answer right away, and that is pretty much everything, except for this very tiny part that is occluded by the sphere. So just like this cone behind the sphere, like literally behind the sphere, that's the part that I don't see. Most think that you get about half the room. Okay, thanks for this. So which is wrong? Why is that wrong? Well, look at the think about the sphere for a second. Look at its side. Well, it doesn't have sides, but go maybe like go to this point here. Okay, so pretty close to the tangent. So what happens to the ray? Well, I got the incoming ray here, and the reflected ray, it goes backward, like it passes by, right? It gives me a point behind the sphere, not right behind the sphere, okay, but it follows kind of the direction, so it doesn't bounce back, right? So there's, like, if you look at the normal, it's not like it bounces back to me, right? So the only part that is not visible in the sphere is the very small part. If I make the sphere very tiny, I can make this pretty much infinitely small. It's just the part that's exactly behind the sphere that I can't see at all. So this is the only part that's missing. So a single sphere gives you almost the entire room. So that's an interesting thing to know. Okay, and that's what we call an environment map. And that's the idea of environment mapping. Well, yeah, you could argue, well, but it sees you. You're also part of the scene. So of course there's occlusion going on in the room. Okay, sure. But yeah, yeah, you occlude what's behind that, but you're also in the mirror. Okay. So getting back to the to my argument is, so this is now an image, a two-dimensional image, right? Two-dimensional image that captures the entire scene as it's visible by the center point. Okay, and you're also visible by the center point, so that's not a contradiction. Okay, so it captures everything except for the tiny part, which we'll conveniently ignore here. So all I have to do is somehow find a way how to map that environment back to the surface as a texture. And remember, I said a texture is not just a two-dimensional sticker put to the surface. Here's another example of a texture where that is certainly not true, because I don't want to have an image of a sphere on my object later on. I want to see the environment. As a matter of fact, you often don't use spheres. So the most popular way to represent an environment is a cube instead of a sphere around a sphere representing the environment around a point. The usual way to go is with what's called a cube map. So the other one is called a sphere map. I would have thought that. So a cube map is the same idea. So I capture the environment around a point, and you can imagine this approach being a little bit different, so that you capture the environment by 6 photographs. Okay, so you place yourself in front of, in the center of your position, your point that you want to the environment to reflect, and I take a photograph left, right, top, bottom, front, back. So I take 6 photographs, and I reassemble them into a cube. Okay, and they're called Y positive, Y negative, so on and so forth. If I would map those properly to an object, such as a sphere here, you can see what this would look. This also tells you how to turn a sphere map into a cube map, and vice versa. And it also shows you that if I look at one sphere, I can actually see all of the faces. okay? Except for the one that's right behind it, okay? So literally just that tiny fraction that is behind it. You notice that Z negative, the gray part doesn't show up here very well, okay? So that's because it's just a tiny ring on the outside. So this is highly distorted, okay? I didn't say that this is this isn't distorted or anything, right? This is super distorted, right? So particularly when you sample that with a photograph, you get a lot of distortion. Large space is mapped to a small area, and larger area is spread out far. So this is also why generally these cube maps are preferred, because they're not that distorted when you capture them. But if you capture a real world, often these light probes, as they're called, these polished spheres are used. Now, if instead of using a boring image such as this one here, I can also use a literally rendered representation of the environment. So I can literally render the scene 6 times from the center of my object that's supposed to reflect the environment. So I simply put my viewing matrix in a way that it creates a camera position inside the object. Then I render into 6 textures. Okay, I said before with the planar reflections, I can render into texture. So I now do this sort of a little bit worse approach. I do this 6 times, create 6 images, and then I store them in one cube map. So there's actually support for that on graphics cards. So instead of having 6 separate textures, you can just say that's a cube map and that's this side. You can also render into that side directly. Now, if I map that using the proper texture coordinates to, for instance, this teapot here, this, I don't know, gold teapot or whatever it's supposed to be, then it'll look like this. And that's a very popular technique. So here is a computer graphics, I would say a game demo setup, but as you can see here, this is a scene from Terminator 2, Hollywood movie, pretty popular one. That movie also used sphere maps, or environment maps in general. It also used environment maps to render the T1000, if I recall it correctly, as it's called, as this silvery, mercury-like thing. Now, as we'll see in a second, the environment map is only correct if you map it to an infinitesimal point, infinitesimal small point. Now, if the point is infinitesimal small, I can't see it anyhow. So who cares? So what we do is we extend the sphere to a certain size, and then the reconstruction starts to be inaccurate. So the larger the sphere gets, the more inaccuracies you accumulate. You can easily imagine that if you increase or decrease the size of a sphere, the reflection should change, right? But since I placed the camera in just one point, my captured data doesn't change. So while the reflection does change due to the computation, but it's not accurate anymore. However, and that's an important point that I want to make here, if you look at that image here, if you deviate even further from the spherical shape to other shapes, such as a human, the reflection will break down even further. So the reflection will be more and more inaccurate. However, and that's really the big however, no one in the world, or hardly anyone in the world, can tell, right? Because we're extremely bad at judging both reflections and refractions for their accuracy. The question is, why are we so bad as humans? Why can't we not figure this out better? Because it doesn't matter, right? This is always my sort of motivation for nature doing something. If it matters for survival, I don't know, fleeing from a tiger or something, we would have developed it. However, there simply aren't any complicated reflecting objects in the world, right? So there hardly are, and they certainly weren't for the most time, for most of the time of our evolution. Right? So this is why we never developed a sense to judge the correctness. And why would it matter, right? I mean, in nature, all the reflections are correct anyhow, right? So we're very bad at judging this. Even extremely simple objects such as spheres. I mean, this is probably the simple most. Maybe a cube is even more simple. We're doing an incredibly bad job at figuring out whether the reflection is correct or not. So that's Act 1. So if we make a mistake, it's probably not going to be a big deal. Certainly isn't here. And there's another very important thing. Sometimes, actually fairly often, you don't want the reflection to be accurate, I would say. Isn't that what we always want? We strive for correctness? No, not always. Here's an example, and that's why I picked that particular scene. In the scene, if you go back, I don't know, if you find Terminator 2 somewhere and watch it and watch that particular scene, what happens here is this T-1000 punches through a hole in the helicopter and then gets its human shape back. What you see is the astonishment in the face of the helicopter pilot reflected in the head of the Terminator. And that reflection is completely wrong. But since we can generate this also wrong in a computer, and we can control it, because this is pretty much a planar reflection here, which it certainly shouldn't look like. The viewers can much better see that. Okay, so yeah, there are situations, for instance, in a car mirror that should reproduce the environment more faithfully, in particular when you design a car. But when you do a movie, you sometimes just want to create a dramatic effect, and you don't care about the correctness. The opposite is the case. I mean, and that is true for so many things which we don't notice. I mean, if you play a jump and run game, you turn in midair, which is obviously not physically correct. You can't turn in midair unless you eject some sort of matter, just like a rocket does. Right? So you can't change your inertia, you can't change your direction. Still, we're totally used to that in a game, right? So accuracy is not the primary goal, the goal that we should also strive for. Okay, let me just do one more slide and finish this in the next stream. We're a little bit over time, but I just want to get this across. So I said that a texture is just basically a mapping. You should forget this idea of it being a two-dimensional sticker onto a surface. And in particular for cube maps or environment map, this is certainly true because our mapping here becomes a little bit more complicated when we go from object coordinates, from a point on the object, to texture coordinates, to color values. Okay, so what do we do, or what do we have to do when we apply a environment map, or more specifically a cube map here? You can imagine the cube being constructed around the object. So this here is where the environment map sits. And if I render this object, what I want to know is, like, say I render this point here. I want to know if this is my camera position, then if it's a perfectly reflecting object, I get incident ray equals exiting ray. So the color that I map to, say, this point here, should be the color that I see here along that direction. Okay, yeah. That I see along that direction here. Okay, so what I want to apply the content of the environment map at this point. Okay, I want to basically apply to that point what does the reflected ray see, and what the reflected ray see is what I've captured before, what I've rendered before. Okay, so what we need to do is, from the incident ray's direction and from the surface position, I need to efficiently compute the texture coordinate of that texel here. If I can figure that out, I'm done, right? I access that side at that position, I'm done, I map it to the surface, I return its value, and I get this appearance of a reflected object. What do I need to know? Well, I need to know the normal, again, the incident direction, that way I can compute the reflectance direction, and I get this surface point. How is that executed? Well, fortunately, there's functionality on the graphics card that's basically a texture coordinate generation for cube map that takes normal incident direction and computes the reflected ray. More on that in the next stream. And then I just need to convert the reflected ray as a vector. I need to convert that vector into, well, 3 components. Sounds easy. Vector is also 3 components. What are the 3 components? Well, the first one is just an integer that says side 1, 2, 3, 4, 5, or 6. And the second 2 are floating point values that tell me where on that side. So what I want is, I want to know which side and where on that side. So where on that side is usually between 0 and 1. Okay, and that transformation from the direction to the texture coordinate is also done by the graphics card, by cube map texture coordinate generation, but it's super easy to do, so you can also do it in the shader yourself because it's such a simple process. And that's what I'll tell you next stream, which is next week, and then we'll then we're done pretty much with the reflections, and we'll also continue with another topic, and yeah, just take it as a surprise. You'll see what's coming. We do have time for questions still. Yeah, so we're about 5 minutes over the original planned time, but anyways, if you have any questions, go ahead. Let me drink something in the meantime and see. Yeah, exactly. So mirrors can do weird things. I mean, literally in nature, where would you expect a mirror in nature? I guess the only thing that I can imagine that would create a mirror is probably like if you think about Stone Age, right? It's probably a water surface. Hmm. And what's the water surface? It's either planar. Yeah, we can judge planar mirrors pretty decently. So it's either planar, or if there's wind, it's wavy. And if you've ever looked at the ocean, you don't see much of a reflection. I mean, you do see, right? Ocean water looks blue, which is because the sky is blue. So you see the uniform reflection of the sky, but that's pretty much it, right? So, and I don't think that there's any other situation in nature where you would have a reflection. Okay, yeah, unless you have wet stones. Okay, sure, yeah. So there might be some awkward situations where you also get mirrors, but that's fairly rare. And what's even more interesting to me is even today. I mean, we're obviously not in Stone Age anymore, even though we sometimes behave this way. But nonetheless, even today, we can create tons of artificial objects, right? But look around you, like literally look around in the room that you're currently in. How many mirroring objects are in this room? Like, okay, there might be some reflective surfaces, like the monitor, for instance, right? If you have a reflective monitor, it's probably going to reflect the environment. But again, it's planar. And there might be a water bottle or something, right? Which to some degree reflects the environment and is translucent as well. But it's actually very rare, which is one of the reasons why it's so popular to do this in movies, right? Why T-1000 or what was it, episode one, that one starship, can't remember which one, like in the beginning of episode one, right? Where, I don't know, the Jedis would fly, that also had a perfectly mirrory surface. This is why movie directors and filmmakers use this situation, because it's so strange, right? It's so alien, literally so alien to us, that we have these reflective objects in a scene, and that's why they get used in, well, I don't know, fantasy movies or so, right? So that said, it's not such a big deal in virtual environment to get reflections not 100% accurate. It's a bigger deal in engineering, right? If you engineer a car and you want to know where is light reflected, does it maybe blind the driver or the plane's pilot? Then of course you're shooting for as much accuracy as possible. Okay, good. I guess that's pretty much it. Then again, as promised, this series will continue next week with the conclusion here, and then we'll talk about other inter-scene effects, inter-object effects to increase realism. Until then, as usual, stay healthy and bye-bye.